In this first part of this problem, we're trying to find the area of region R, and we're going to use integration to do that. And basically what we can do is we can create infinitely thin rectangles that are going to stretch from the upper boundary down to the lower boundary. And we can see that there's no change in the boundary as we scan this rectangle from left to right. So we can integrate along the x-axis. So we're going to say that the width of each rectangle is dx, and we'll integrate from 0 to 2 to find the area. Now, we do have to, in this problem, determine which of these boundaries goes with each of these functions that were given. The lower boundary here definitely looks like a cosine function that's been shifted downward, and so this is going to be our g of x. The upper boundary looks like it is a downward opening parabola with a vertex at 1, 6, and that indeed is what we have for h of x. Okay, so what we're going to do is we're going to say, okay, if we're going to find the area, we are going to integrate from 0 to 2. We are going to say that the height of each one of the rectangles, the width is dx, but the height is going to be the difference between h of x and g of x. So we're going to say that this is going to be h of x minus g of x. And so that is how this is going to unfold as we work the problem. We'll break this up into two separate integrals. I'm going to go from 0 to 2 of h of x dx minus, and then we'll integrate also from 0 to 2 of g of x dx. So this is going to be the setup that we're going to use. All we're going to do now is go ahead and substitute in these functions. So what we've got here on the first one, from 0 to 2, my h of x function is 6 minus 2 times x minus 1 squared, and that's going to be multiplied by dx, then minus the integral from 0 to 2 of g of x, which is negative 2 plus 3 cosine of pi over 2x. And we, of course, have to put this in parentheses and multiply it by dx because that's the width of each one of the rectangles. Well, it's just now a problem of working through these definite integrals. Here what I'm going to do is expand this binomial and distribute the negative 2 at the same time. So I'm integrating from 0 to 2. This is going to end up being 6 minus 2x squared plus 4x minus 2. So that's what I have here. On the next one, I'm integrating from 0 to 2. And I'll just go ahead and rewrite this. And now what we're going to do is we're going to go ahead and take the antiderivative of both of these and then evaluate it using the fundamental theorem of calculus. On the first one, here we are going to combine the 6 minus 2 into one term, but the negative 2x squared, taking its antiderivative, takes us to a negative, and I'm going to erase this because we're going ahead and taking the antiderivative. This is going to be, this will give us a negative 2/3 x cubed. The antiderivative of 4x would be 2x squared. 6 minus 2 is 4, and that antiderivative is a negative 4x. And what we're going to do is we're going to evaluate that from 0 to 2. Over here, when I take this antiderivative of negative 2 is negative 2x. The antiderivative of cosine pi over 2x, well, I have to divide by pi over 2. And what this is going to end up giving us is 6 over pi times sine of pi over 2x. Because the antiderivative of cosine is sine, but I do have to divide here by the pi over 2, and that gives us 6 over pi. I do need to evaluate this one, and also between 0 and 2. And I notice I still have brought down my minus sign here. Well, the math here gets pretty easy when you see that plugging in a 2 here is going to give me negative 16 thirds, and this is going to end up being plus 8, and this should be a plus 4x up here. This would be a plus 8 and a plus 8. When we evaluate this other one on here, when I put a 2 in, obviously going to get a negative 4, so I'm going to put a negative 4 here. But when I put in a 2 here for x, that's going to be sine of 2 pi over 2, or sine of pi, which is 0. And if I were to put 0 in, I'm going to get 0 plus sine of 0, which also is 0. So really all that I get in evaluating using the fundamental theorem of calculus on the second one is just a value of negative 4. And so when we throw all of this together, it's going to end up being 8 and 8 is 16 plus 4 is 20. It's going to be 20 minus 16 thirds. And when I do that, I'm going to end up with 44 thirds as my final answer for the area of region R. Moving now to part B, it's asking us to find it's asking us to find the volume of a solid that has a cross-section that's perpendicular to the x-axis. So that means then I'm going to have these a three-dimensional figure that's coming out with its base being this line that's perpendicular to the x-axis coming up out of the paper towards us as a third dimension. But this really is a pretty simple problem, because we know that when we're dealing with cross sections, we're basically just going to integrate the area, right? And since the base cross sections are perpendicular to the x-axis, that means that their widths are going to be dx. So that means we integrate along the x-axis, in this case from 0 to 2. All that we have to do then is put in what is the function for the cross sections, which was given to us. So it's very straightforward. 0 to 2, 1 over x plus 3 dx. Now you could straight away know that the antiderivative of 1 over x plus 3 is the natural log of the absolute value of x plus 3. But I'm going to go ahead and use u substitution. I'm going to let u equal x plus 3. Therefore du would be equal to dx. That means I'm going to get a transformed integral that's going to be 1 over u du. And I'm going to transform these limits, right? These limits are in terms of x equals 0 to x equals 2. But since we've transformed our variable into u, when x is 0, u is 3. And when x is 2, u is 5. The antiderivative of 1 over u is the natural log of the absolute value of u. And I have to evaluate that between 3 and 5. So this gives us the natural log of absolute value of 5, which is 5, minus the natural log of the absolute value of 3, which is 3. Combining those using my rules of logs, I get the natural log of 5 thirds. And that is my volume. Moving down to the third part, part C. We now are going to be calculating volume done by rotation. But in this problem, we only have to write the expression for the volume and not really evaluate it. Now the axis of rotation is the line y equals 6. That is going to be this line right here, passing through the vertex. Now, what we're going to do here is we're going to use this fact here that when we do an integral by rotation, we are going to say that the volume is pi times the integral of big R squared minus little r squared. And in this case, it's going to be dx because my axis of rotation is horizontal. So what we do here is, what is big R? Okay, that is going to be the distance from the axis of rotation down to the furthest boundary. And the little r is going to be the distance that would go from the axis of rotation to the nearest boundary, right here. So this is going to be little r, this is going to be big R, like that. So we can come back here and say, okay, well, let's just figure out what these are. So we can say pi times, we're integrating from 0 to 2, so we're going to add that in. Okay, well, big R. Well, what is this distance here? Well, it's going to be this function, 6 minus this lower function, which we called g of x. So this is going to be 6 minus g of x, and that is squared, minus, okay, the distance r. Well, that's also going to be 6, right? So we're going to take 6 minus, and that would be the distance that we would stretch to this boundary here, which was h of x. And then we have to square that. And then this whole thing is multiplied by dx, because each one of these vectors that we're stretching down, and then we're going to end up rotating them around here, they have a width of dx. And that right there completes this problem, because all we had to do is write the expression that represents the volume. Alright, I hope this was helpful. If it was, please like this video and feel free to subscribe to this YouTube channel. Thank you.